Dudley. Dudley. Dudley.
Hey.
We normally meet at 9:30, right?
Yeah, I know.
Okay. All right. All right. You don't have to be in here till 9:30. All right.
Oh, okay.
No, I just basically I lost my presence of mind, and all of a sudden I thought, does it start at 9 or 9:30? So I opened it early today. All right.
Yeah, I just opened mine early too. I'm like, oh, okay.
You can do whatever. I'm not going to start till 9:30 though. Okay.
All right. Okay, thank you.
All right.
All right.
Nope. I'm about to start teaching. Oh, I'm sorry. I didn't know you were starting. 8 minutes. Okay. All right. So when you have your phone connected to it? Oh. You have to hear me. Not before. Good. Hi, Charlie. Hi, Charlie.
Hi, Mr. P.
Yeah, sorry. I lost my presence of mind. I didn't know what, I forgot whether we did this at 9 or 9:30. So I opened
No
this
worries.
up early.
I was nervous when I logged on and saw it that it was already sent. So, but it's okay.
No. That's the reason. What do you need with this, with the Lewis dots and the VSEPR?
What do you mean exactly?
How confident do you feel with it? Do you want this to be a workshop? Do you want me to go through an actual lesson?
Yeah, I mean, yeah, that would be just,
No,
I feel like the usual. What is different about this one?
Well, have you had VSEPR yet? Have you had?
Yeah.
You've had this in your lecture.
Yes, yeah, we have. So this is one that I feel more comfortable with. I honestly had more issues with the heat vaporization one. So.
Okay, so you're in Dr. Musgrave's class.
No, I'm in Warden's class.
Okay, and Dr. Warden's got all the way to intermolecular forces?
Yeah, we covered that like a week or 2 weeks ago.
What are you doing now then?
I'm supposed to take notes on it today. I'm not sure.
Okay.
Let me see.
Hi, Trin.
Also, did you get my email at all?
About when did you send it?
Last week. About, you wanted me to stay after and talk about something, but I lost service and
okay. Is that let me I don't want to share screen. Hi, Trin.
Hi, Professor. How are you doing?
I'm doing fine.
Hi, Charlie.
Hi, Tin. How are you?
I'm good.
All right, Samir's in here.
Is this our last class?
Yes, it is.
Because I was looking at the lab final date and
next week.
Next week, yeah.
Next week.
So we have VSEPR lab due after
it's
final, right?
No, it's due next Wednesday at midnight.
So then when is our final due by?
It'll be from 8 to 5 next Thursday. Charlie, I misspoke. Your last name is Baden, right?
Baden, yeah.
Baden, okay. Depends upon which German dialect you check.
Exactly.
Charlie, I'm sorry I misspoke. I have another Charlotte, and she was in trouble. You're not doing too badly, okay?
Okay.
You scared me. No, I apologize. There was something, I was looking at this and I was looking at the grades and thinking, oh my God, she has what score? And it just freaked me out. And then I managed to freak you out. Right now, after the TLC thing, you've got an A. Okay?
After this past one?
No, after the TLC, after the chromatography report.
Oh, well, I don't know about after this past lab, but we'll see.
The heat of vaporization.
Mm-hmm. We get our lowest grades dropped though, right?
Yeah. Mm-hmm.
Okay.
Yeah. Your lowest pre-lab, your lowest report, and the lowest results, and your lowest post-lab. They each get dropped, and it doesn't have to be the same experiment.
Okay. Cool.
So you're in good shape.
Thank you.
All right. So, yeah, Charlie, you don't know where you're at right now, right?
Oh, that's what I was doing. No, I was going to check. Hold on.
Faye, Trin, Samir. Let's see who else is in here. Javier, I'm at your disposal. I can give you a lesson on VSEPR and I can do a lesson on VSEPR and Lewis dots. if you'd like. If you feel comfortable with it, then I can just make this like a workshop. What is your disposal towards this? My class last night wanted to go
dot structures, but I did have some questions about the other like data for the table.
That goes without saying, Faye.
Oh, sorry. I thought you were.
That goes without saying because that is confusing as hell. I know what you're talking about. You're talking about the AX2E thing. Is that what you're talking about?
Honestly, I was talking about the and kind of like the polar, if it's polar or not. I mean, it says it on the table, but I don't know why.
Okay, no, I can get through that.
I mean, besides the shape.
I'm trying to get a basis here. Okay, I'm trying to get the lowest common denominator here. Is there anybody that would like me to go through Lewis dot structures again? I can do it real quick. Are you familiar with formal charge and why it is necessary?
I would like to do a review on that real quick.
Okay. Anybody have an objection, guys?
Not for me.
Okay, so I'm sorry. Those of you, just bear with me, all right? Let me do something first, okay? If you guys, I'm not taking attendance today, so if you want to bugger out at any time, feel free, all right? But what I do want to do is I want to share screen and get into the course, okay? And I want to get out of here real quick. And yeah, I want to go to content. Okay, this is confusing as hell. And I have no idea why he did it this way, but it is what it is, and you're going to have to deal with it. Be prepared, 90 questions on the results. 90 questions on the results, 5 on the post lab. All right. Post lab, I'm going to do that first. Very, very simple, guys.
Did you say 90 questions?
90.
On the VSEPR post lab or VSEPR results?
Yes, that is correct. It's going to be good practice. It's good practice for you, but it is what it is. And I don't know how he's justifying this because the post lab, it's like doing the post lab gets you kind of extra points because the post lab's normally worth what, 30 points? Whatever, it's worth like 30 points and you only have to answer 5 questions for it. But for the results, you have to answer 90. Okay, so post lab, you're given a compound, NH2Cl. You need to figure out, question 1, determine how many valence electrons are there. Question 2, in the entire molecule, how many lone pairs of electrons? Now, when you get asked questions like this, you have to look at the question very, very carefully. All right, you have to decide, first of all, do they want lone pair electrons or do they want lone pairs? This one is specifically asking for lone pairs. The second question you have to decipher is, are they talking about the whole molecule or are they talking about the lone pairs about the central atom? This one, I would answer it like lone pairs around the entire molecule. Does that make sense to you guys? This is just one of those points where you have to be very careful about what is the question asking you.
Yeah, that makes sense.
Okay, how many bonds are in the NH2Cl? In other words, how many This is another question you have to be careful of. It's like if you had the chance to be taking this with the professor in a test. Does a double bond count as 1 or 2? That's the kind of question you would ask the professor if it's a face-to-face thing. It becomes a little more problematic when it is a off-site test like this. The bonds mean how many okay, a bond is consisting of a pair of electrons. I would interpret this question to be, how many bonding pairs of electrons are there? The answer is going to be 3 in this case anyway. So each one of these are single bonds. The H's are single and the Cl are single. And again, why does he do this? You know, straight off the bat, there aren't 20 bonds in that thing. Why does he do that? All right, what is the shape the atoms make? That is the molecular shape. And last question, is the molecule polar? That's the entire post lab. The results is going to be 90 questions. Questions about this portion of it.
When you're talking about number 3, I think.
How many bonds?
Yeah, if you draw the Lewis dot structure, you count the number of, like, you know, when you do the central atom and then you write the other ones around it and you connect it with the line, which is technically 2 electrons, you count those lines, right?
Yes.
Is that what you're saying?
That's what I'm saying.
Okay, thank you.
So 5, 12, 13, 14, there are 14 electrons. Minus 6, there's 8 left, 1, 2, 3, 6. Okay. All right, so.
How do you determine the central atom again?
The least electronegative. I'll go over that, Max, okay?
All right. Yeah.
I promise I am going to go through Lewis dot structures and how you make this determination. And if you choose something other than the least electronegative, what happens is the formal charges get outrageous. And I'll get into formal charges as well. When we're talking about bonds, basically, if you want to think of it as the lines, when you're drawing a Lewis structure, think of it like the lines between the atoms. That's what they're talking about. Okay, Charlie? Charlie?
Yeah, I'm here.
Did you get what I just said?
Oh, sorry. Yeah, the lines between the Lewis structures.
It's
between
lines can act as an electron pair. Or in this case, a bonding pair of electrons. Okay, so we're going to get into the other thing. The other thing is a lot more confusing. That was simple. Results of this. Okay, so first thing we have to do, whenever you're answering questions, we're talking about VSEPR, the first thing you have to do is you have to draw the Lewis dot structure of the particular atom. So if I'm doing water, can you see my drawing?
Yeah.
All right, that is my Lewis dot structure. So I'm going to base my answers all upon this. Now, how many lone pairs, non-bonding electron pairs does the compound possess on all atoms? Okay, so the hydrogens do not have any. The oxygen has 2. So the answer is 2 lone pairs. Understand that understand that the question is asking for lone pairs, so answer it in that fashion. All right, now here's the confusing part. All right, we're dealing with this Lewis dot structure. You're going to have to answer 4 questions on that. The number of electron groups around the center atom. Electron groups are called electron domains, electron clouds, and they consist of one lone pair of electrons counts as one domain. A single, double, or triple bond also counts as one domain. A triple bond counts 1 electron domain. Double bond, 1 electron domain. Single bond, 1 electron domain. So if I'm looking at my oxygen, I have 1 domain from the bond between the oxygen and the right hydrogen, 1 between the oxygen and the left hydrogen, 1 lone pair, 1 lone pair. There are 4 electron groups around that oxygen. Number of atoms bonded to the central atom, 2 hydrogens. Number of non-bonding electron pairs, lone pairs attached to the central atom. There are 1, 2. General formula. Now here's where it gets tricky and dicey. What he is doing, he is counting the central atom as A. If you have an atom bonded to that central atom, he designates that with X. So in this case, my general formula is going to be A for the oxygen. The 2 hydrogens are going to be X2. And the other lone pairs are designated as E2. So in this particular example, we have 4 domains around the oxygen. We have 2 atoms bonded to the central atom. We have 2 non-bonding electron pairs. And the general formula is AX2E2. This should be the correct answer. Do you understand how this is working?
Yeah.
Are you glad I explained it?
Mm-hmm.
Yes.
All right. Again, there is an absurd amount of choices. All right. The electron group, I call it the electron geometry, or you can think of it like the overall shape, and hybrid orbital designation. I will get into hybrid orbitals as well. Okay, there are 4 things around, 4 electron groups around the center atom. That dictates that it is a tetrahedral. With 4 groups around it, you need 4 atomic orbitals to be hybridized. They start off SPPP or SP3. Okay, what is the molecular shape? This one, you got to kind of like take the overall shape, the electronic geometry, and you have to subtract out in your mind. You have to subtract out the lone pairs because you can't see them in the molecular shape. So there are 4 things attached to the center atom. I can't see 2 of them. So that shape becomes angular or bent. Last question, is it polar? This is water. It has polar bonds and it is asymmetrical, which are the 2 things that are required for a molecule to be polar. So yes, it is polar. And you go through all the other compounds. Each of the other compounds has these same 5 questions. And there are 18 compounds. So you have a total of 90 questions. In case you thought I was lying, There's the 90th question. Anything about the way that the results are asked and the way you're supposed to answer them? Any questions about that? In that case, I've had a request for some people to go through Lewis dot structures. I've had requests from other people to do something on polarity. What other subject matters do you want to talk about here?
Yeah.
Could we just go over like a, oh, go Charlie.
Sorry, I was just gonna say yesterday's lab.
I'm sorry?
I have a request for yesterday's lab.
Okay. Any objection to my going back and doing that? Come on, guys, speak up,
No.
because I'm kind of getting into your time. Having heard no objection, I'll go back and do that. Okay, so we're dealing with, you talking the results, Charlie?
Yes. And then mostly because I got the post lab like completely wrong. So I have a feeling I got the results wrong as well.
Yeah, I think one of them was really a toughie to figure out mathematically. I think the last one.
Yes. I think I went through that with you, and that has to do with the conversion of the logs.
Yeah, that was hard.
All right.
Like I rewatched your video and everything, and I walked through it myself. But every way that I tried it, the answer didn't make sense.
So what you're saying is that I'm confusing. You're blaming me, is what you're saying.
Yeah, exactly.
Okay, I can live with that. What do you want? What do you want? Results or post lab first?
Results, probably.
Okay, we're going to go through that first. All right. And I got to get this out of here. All right, I'm not going to try, where? You are seeing the screen, correct? Guys?
Yeah.
Yes.
All right, results. Why is this not, I know why. Okay, I'm sorry, I've got to get in. Oh, crap, I could have done it. I'm sorry, what happens is the time frame for turning in the report is done, so it blocks me as well as you. That's what's happening here. All right. Sorry about that. Okay. We have, do you have your data?
Yes, I do.
Okay. What was the boiling point? Should have been about 82, 81, 82 degrees Celsius.
The average is 81.85.
81.5?
0.85.
81.9. Okay. In K, you add 273.2 to that. And I got 355.1. Right?
How much did you add to it? 273.2. Okay, I just did 273, but yeah.
All right, so it's 355.1. It's not going to matter that much. All right. So that's the boiling point in K. Atmospheric pressure, I believe, was 760.2 or something like that.
Yeah, 760.2 mmHg.
Okay, so that's going to be torr. mmHg is the same thing as torr. I'm just trying to figure out where we're starting from. All right, now the Clausius-Clapeyron. I got ln of P1 over P2 is equal to negative delta H over R times 1 over T1 minus 1 over T2. Is that correct, ladies and gentlemen? Talk to me, is that correct?
Yes.
I need to.
Wait, is the change in H over R, is that negative?
Yes. The
Is
way,
that
the way I have drawn the formula, yes. Remember, I told you that the formula can be manipulated. Remember, I told you that. And I told you to find one formula and stick with it. All right, we're going to go. The one that's in the book is P2 over P1. Ln of P2 over P1 is equal to negative heat of vape over R times 1 over T2 minus 1 over T1. All right?
Yeah, that sounds right.
All right, so what do you want to be your second parameters? Do you want the 295 to be your second parameters, or do you want the 355 to be your second parameters?
355 is the second parameter.
Okay, so you
Wait,
don't know
no,
what the...
Sorry, 295 is the second parameter.
You don't know what the pressure at 295 is, but you do know the pressure at 355 is 760.2. That's equal to. Now, what you had to do is you had to go to that chart. You knew the boiling point was 81.9, and you had to figure out what the heat of vaporization was. And that should have been, I believe, 40 point something.
It was 44.0.
44.0?
Yeah.
That's in kilojoules per mole.
Yep.
Mm-hmm.
R is 8.31 joules per mole degree centigrade. From that, I am taking 1 over 295 minus 1 over 355.1. Are you seeing what I have there?
Yeah.
Does that look like how you set it up?
Well, don't you multiply through by 1,000 for the 44?
Yes. But if you notice, I have kilojoules and joules.
Yeah.
All right, so I have to change one to the other. Okay?
Mm-hmm.
So I'm going to change this. All right. So I've changed it to that. I've just divided by 1 by 295 and 1 by 355.1, and I multiplied my kilojoules by 1,000. Are we good here?
Yeah, makes sense.
So I did this math out and I got negative 5294 times 0.00058. That ends up equaling a negative 3.07. And that's equal to the ln of P2 over 760. Are you all there with me? Come on, I need to hear some feedback.
Yeah, I'm trying to figure out if I am, but yeah, I think that makes sense.
All right, now here's the funky thing. A lot of you, what you do is you take this 760 and multiply it by negative 3.07. You cannot do that because it's the ln of P2 over 760. So you have to raise e to the ln of P2 over 760 to get rid of the ln. If you do it to the left side, you have to do it to the right. This is what you have to do. You have to take E, raise it to the ln P2 over 760 is equal to E to the negative 3.07. E to the ln, E raised to the ln is equal to 1, so it goes away. And you have P2 over 760 is equal to E to the minus 307.
That makes sense.
So you get P2 over 760 is equal to 0.0464. P2 So I get P2 over 760.2 is equal to E raised to the negative 3.07. P2 over 760 is equal to 0.0464. 760 times 0.0464 is equal to 32.3 or 35.3. Okay. Are we good with that?
Yes.
Charlie, are you okay with that?
Yeah, it turns out I got it right, so I'll take it.
Good enough. Now, you needed to do a picture on Excel, and the picture, you needed to put the slope. If you did it on Excel, you got the equation for the line. What you have to understand is that the slope of that line, negative the slope of the line, I'm sorry, wait, time out. Let me erase it. The slope of the line is equal to negative delta H over R. So in order to get the delta H, whatever slope you got from your graph, it's going to be a negative number. You multiply that by negative 8.31. This gives you the joules of the heat of vaporization, and it should be in the tens of thousands. You simply take that number and divide it by 1,000, and you get your heat of vaporization in kilojoules. Are we good?
Makes sense.
Okay. Are we good with this, guys? Any other questions on the results portion?
You don't have to go through a whole problem again, but I wanted to know how to do it if you're missing one of the temperatures.
I'm going to go through and do the post labs.
Okay.
Fair enough.
Sure. Yep.
Okay. PostLab, I think, had 2 questions on it. One replicated what you just did, and the other one, you didn't know what the boiling point was. Am I correct?
Yeah.
Yeah. I just forgot how to do the algebra because I didn't know how to isolate T2.
1 second, I'm going to answer that because somebody may be missing class. You have it? Okay, thank you. Okay. My guess, guys, is if you haven't had one of these questions yet in your lecture, you will on the next test. I suspect that. Okay. First one is a gimme. They give you the experimental and known value, determine the experimental error. So I'm not going to get into that. An unknown liquid has a heat of vaporization of 39.72. Okay, if the normal boiling point is 88, 88 plus 273 is 361. Okay. What is the vapor pressure at 25? So that's the way I set up this problem. I've got my first pressure, which is boiling point, which is atmospheric. That correlates to the first temperature, which is 88 plus 273. My second pressure, I don't know, but I do know my second temperature. So I set this up like this. Okay, I just want to check my math here for a second. Okay, so I get it to this point. 1 divided by 361 is this number. 1 divided by 298 is this number. I changed my delta H vape to joules, divided it by 8.314, came up with that number. I subtracted these two. What?
Is the normal boiling point always going to be the top pressure?
You could. It doesn't matter. Believe it or not, if I take this 760 and put it down, but put the 361 on the second number here, the math works out the same.
Okay.
Because what happens when I subtract these two as they are right now, I have a negative number times a negative number, right?
Yeah.
Okay. And that's going to correspond with the ln with 760 over whatever P1 is. If I switch these two, I have a negative times a positive. That means that my answer here will be a negative. which is going to correspond to the ln of P1 over 760. Does that make sense? Mathematically, it works out.
Okay.
All right. You can do one of two things. You can trust me on this and just memorize the equation, or you can go through and try it yourself. In this case, what you would do is you would take the ln of P1 over 760, and over here you would take 1 over 298 minus 1 over 361 and work it out and see if it works out to be the same.
That's fine. That's how I did it. I just got it wrong, so that's why I was curious, but that makes sense.
So you can put the pressures and temperatures in any order and it doesn't matter?
I didn't say that. What I told you, if you remember correctly, when I told you about this yesterday, I gave you 3 formulas. All 3 of the formulas are valid. What I told you was pick one. Okay? Pick one and stay with it. I'll show, who's asking the question?
Max.
Max, I'll show you what the 3 formulas are in a second, okay? And all I'm going to tell you is to pick one of them. Mathematically, they will work out to give you the same answer. You're just going to have to trust me on that, okay? Okay, I'm sorry, I'm just doing the math here. Okay, the math. I multiply this number times this, I end up with 2.82, a positive 2.82. That's equal to the ln of 760 over P1. I raise both of these to the e, raise e to that power. So e to the ln 760 over P1, e to the ln goes away. That just equals 760 over P1. E raised to the 2.82 equals 16.8. Multiply both sides by P1, I get 16.8 times P1 is equal to 760. P1 is equal to 45.2. Did you see how the math worked?
Yeah, that makes sense.
And everybody else, Charlie's being the spokesperson for you all. Are you all seeing how this works?
Yes.
Yes.
All right,
I
now,
just have dogs in my background.
don't worry about it. My dog's going crazy myself. Okay, now, an unknown liquid has a heat of vaporization of 8.100 kilojoules per mole. That means I'm going to change that to 8,100 joules per mole. That gets divided by 8.314. Now, if my vapor pressure at this liquid at minus 199 C is 115 torr. So I put 1 over 273 minus 199 is equal to 74. Times 1 over x. Okay. Sorry, I got to get this out again. All right, this ln of 115 over x. Okay. Now, if I'm setting this problem up, nope, that is wrong. All right. It's telling me the heat of vaporization is 810 kilojoules per mole, and it's saying the vapor pressure at minus 199 is 115 torr. What is the normal boiling point of this liquid in degrees Celsius? Normal boiling point, pressure is 760. So I'm going to put the Ln of 115 over 760 is equal to 8,100 joules per mole over 8.314 times. The top one pressure was 115. The temperature, minus 199, is 74 degrees Kelvin. 1 over 74 minus 1 over x. So I do the Ln of 115 over 760. 115 divided by 760 is equal to 0.151. 8,100 divided by 8.314 is equal to 974. 1 over 74 is equal to 0.0135 minus 1 over x. So all I did here, divide the 115 by 760, so I have the Ln of 0.151. That's equal to, I divided 8,100 by 8.314, came up with negative 974, times divided 1 by 74, came up with that number, minus 1 over x. Are you with me?
Yes.
Yep.
Okay, the Ln of 151, I'm just punching the Ln button, 0.151. That is equal to a negative 1.89. Negative 974 times 0.0135 is equal to negative 13.1 minus or plus 974 over x. So all I did, punch in Ln 1.89. I'm sorry, excuse me, Ln 0.151. That ended up being a negative 1.89. Okay, I multiplied negative 974 by 0.0135. I ended up with a negative 13.1. Negative number times a negative number makes a positive number. This gives me 974 over x. Add 13.1 to both sides. Added 13.1 to both sides. I ended up with a positive 11.2 is equal to 974 divided by x. Okay, so I did this math out. I got 11.2 is equal to 974 over x. Therefore, 11.2x is equal to 974. X is equal to 87.0, but that's degrees Kelvin. You got to change it back to degrees C because the question asked for it in C. So 87 is equal to 2C plus 273. Negative 186 is equal to C. Who was asking for this in temperature? Solving for it in temperature.
I was. I can't see your paper that well. Sorry.
I'm sorry. I'm okay. I'm focusing it. Is it focusing good or bad?
It's okay. It's really small, like because you're sharing your screen right now, so it's just in like that top bar with all like the small stuff.
Let's try this then. I'm going to stop share for a second.
Perfect. Yep. Let me just look
That
at
look
it
better?
for a second. So, okay, so you multiply. All right, I got it.
Are we good? Max, we good?
Yeah.
Now, one other thing I wanted to share with you. Okay, Max. Max.
Yeah.
There are three forms that the Clausius-Clapeyron equation can be. You can have ln P2 over P1 is equal to negative delta H vape over R times parentheses 1 over T2 minus 1 over T1. That is mathematically equivalent to if I switch these two around and switch these two. The ln of P1 over P2 is equal to negative delta H vape over R times 1 over T1 minus 1 over T2. That is also equivalent mathematically to ln P1 over P2 is equal to a positive delta H vape over R times. Notice I've switched these positions. 1 over T2 minus 1 over T1. All three of these are mathematically equivalent. And you may see if you go to a text, if you go to some Google site, you may see any one of these three forms, depending upon the whim of the person that's writing the paper. You may see any one of these equations. They are all mathematically equivalent. What I told you to do, and what I told you being you, the class, is pick one of them. Pick one of them, memorize it, and then use it consistently. Does that make sense, guys?
It makes sense, but now my concern is how do I find out which one is T2 and T1 and P2 and P1?
All you have to do is make sure that, pick one. Which one do you want to use, Max?
First one.
All right. Then, whatever temperature you choose to put in the first position here goes on top. Okay? Say you're asked the question. A sample boils at 200 degrees Celsius. What is the vapor pressure at 300 degrees Celsius? Not Celsius, 200 degrees Kelvin. What is the vapor pressure at 300 degrees Kelvin? At 200, you know, it boils. So you're going to put the 760 on top. That position is where you put the boiling temperature, 1 over 200 K. You don't know what the what the vapor pressure is at the other temperature. But you know what the other temperature is. It's 1 over 300 K. Does that make sense, Max?
Okay, so if they give you a pressure, that they give you a boiling point temperature, you pair that with
760.
pressure. Yeah.
You
okay.
pair that with 760 always.
Okay.
A little more confidence, Max? A little more confident?
Yeah.
Okay, do I have to get through any more of this last lesson?
Can I just see the last bit of work for the one we went over for the post lab? What they did, where we're finding the temperature? I just want to make sure, just the bottom part. Yeah. So you subtracted 273 from
Because
the.
When you solve for X, you solved it in Kelvin.
Okay.
So Kelvin is equal to C plus 273. So I subtracted 273 from my Kelvin temperature to get my Celsius temperature.
Okay. Sorry, I'm just gonna try and.
No.
So then 87 might, okay. Thank you so much, Professor.
No, hey, this is literally speaking. Remember my welcoming note when I said, I am here to help you. If this is doing you more good than my talking about VSEPR and Lewis dots, then God help us, okay? That is wonderful. I'm trying to make sure I do some good for you, all right? Speaking of which, shall we go on to VSEPR now? And
Yeah.
Lewis dots.
Yes.
Okay, I'm going to need to go back to slideshow from beginning. All right. Here are the rules. Guys, I'm sure you've had this in one form or another. You're going to be given, you have to be given a molecular formula. From that, you write down the elements, put the least electronegative in the center. Add up all the valence electrons. Account for charges. What I mean by account for charges, if I have something like SO4 2 minus, my sulfur has 6 valence electrons. My oxygen has 4 times 6. But I have to account for the charge. The charge gives me 2 more because it is a -2. So I add this all up. I have 32 valence electrons. When you have an ion, you have to add the charge as extra electrons, extra valence electrons. On the other hand, if I have a positive ion, my nitrogen gives me 5, my hydrogen 4 times 1. Now I have to subtract 1 because it's a positive charge. I took 1 valence electron away from this. So I get 9 minus 1. I have 8 valence electrons. Is we good with this?
Yeah.
All right. Once I count up my valence electrons, I put 2 electrons between each of the elements. I have to do that because they're bonded to one another, and the least amount of electrons that I can put between 2 atoms and have a bond is 2. So I put 2 electrons between each of the elements. I subtract the bonding electrons I used from the total number of valence electrons. Then the next thing I do is I fill all of my valence electrons, all of my terminal atoms with as many electrons as it takes to get them to 8. Unless we're dealing with hydrogen, and hydrogen, if it's bonded to something else, has the 2 electrons it needs. Hydrogen only needs 2, everything else needs 8. So I'm going to subtract all those lone pairs around the terminals from the remaining electrons. If I have any electrons left over, they go on the center atom. If the center atom does not have 8 electrons, I'm going to take a lone pair from one of the terminal atoms and place it between that terminal and the center atom. I've created a multiple bond. Last step, go back and check to make sure everything has 8 electrons around it. So, as an example, I'm going to go through SO2. SO2 has, putting the elements down, sulfur is less electronegative than oxygen. I put sulfur in the center. Count up all the valence electrons, account for charges. No charge, 6 valence from sulfur, 2 times 6, 12 from oxygen. I have a total of 18. Put 2 electrons between each of the elements. I've now used up 2 here and 2 here. I started with 18, used 4. That leaves me with 14 left. I take my electrons. I take electrons in terms of pairs. Apply them in pairs. And I put left electrons around each of the oxygens so that each oxygen has 8 around it. This oxygen has 1, 2, 3 lone pairs, 1 bonding pair, 8. This oxygen, 3 lone pairs, 1 bonding pair, 8. I subtract. I just put 12 more electrons on there. I subtract it from the remaining electrons I had. I got 2 left. Those 2 go on the center atom. Now, what is wrong with that molecule?
Are we supposed to have those pairs right next to the S?
This pair belongs to this S. Those 2 belong to the oxygen. Those 2 belong to the oxygen.
The sulfur hasn't completed the octet, so you need a double bond.
So I got to choose, got to grab one either from this side or this side and put it in between. Who was asking the question about whether the electrons were around the sulfur?
I was saying about the inner ones.
So who's
the inner
talking?
Samir?
Samir. The inner ones. What are you talking about? This one?
Yes.
Those are the bonding electrons.
Oh, I see. You haven't put the lines. Okay, that's what confused me. Because normally
I'll explain that in a second. All right. So I got to take, as Max said, I got to take this lone pair, put it in there. I've now created a double bond. Now, if I look and count all the electrons around all of the atoms, each one of them has 8. I hate dots. I hate dots because what happens is dots get smudged, and when I look and see a smudged dot, I asked myself, did they really mean to put that dot in there, or is this an erasure or what? So you know when a smudge becomes an electron? When the student wants it to be. I hate dots. So, as Samir said, a line can be substituted for 2 dots. So if I have two dots here, I can substitute a line for it. 2 dots, another lone pair, I can put a lone pair around that one. I have 2 dots and 2 dots, or 4 dots, a double line. 2 dots, a single line. Another lone pair, single line, single line, single line. So I can represent this as everything with lines. Now, it depends upon your teacher. It depends upon your professor, how they choose to write this. I've seen some people that will put lines for bonds and dots for lone pairs. I've seen people put lines for lone pairs and dots for bonds. I've seen all dots, I've seen all lines. They're all really acceptable. Samir, my guess is he uses lines for bonds and dots for lone pairs. Am I correct?
Yes.
It's just the person's choice. And literally speaking, you got to go up and ask him, do you mind that I do it this way? Because if they want it done in a specific format, then you got to do it in the format they want it in. Fair enough?
Yes.
Okay, now let's see where I'm at here. I'm going to do that in a second. All right. I'm going to deal with something called formal charge right now. And formal charge is the charge on the atom as it exists in the molecule. That's what specifically formal charge is. And the way you calculate it, you take your normal valence electrons, the number of valence electrons on that atom as it exists in the periodic table. From that, you subtract out again, remember I told you got to be careful about the terminology. You got to subtract the lone pair electrons plus the bonding electrons divided by 2. So let's figure out what the charges are on the left oxygen. How many normal electrons are around oxygen, valence-wise?
6.
How many lone pairs are around this oxygen?
3.
2.
Lone pair electrons, not lone pairs, lone pair electrons.
4.
4. How many bonding electrons are on this oxygen?
2.
How many?
4.
4. Bonding electrons, not bonding pairs, bonding electrons. So the formal charge on the oxygen to the left is 6 minus 4 plus 2, 0. Let's look at the sulfur. Sulfur has how many normal valence electrons?
6.
6. Now, How many lone pair electrons does this sulfur have? Got to be able to recognize it, guys. I know it's a little bit off. That look better to you? How many lone pair electrons are around the sulfur?
8.
8?
2 pairs. Or 2
Okay,
electrons.
understand. These 4 electrons are bonding. These 2 electrons are bonding. If electrons are between atoms, they are bonding electrons. What I'm asking for are the lone pair electrons. Those are the ones controlled specifically by sulfur.
Just one.
That, how many electrons? Not pairs, electrons.
2.
2. Now, how many bonding electrons between this oxygen and this sulfur?
2.
Count the dots. Not bonding pairs, bonding electrons. How many bonding electrons are there?
4 electrons.
4. How many are on the other side?
2.
So I have 4 plus 2 or 6. And I have 6 minus 2 plus 3. I have a 1 plus formal charge on that sulfur. Let's count the right oxygen. How many valence electrons?
6.
6. Thank you. By the way, there should be 2 dots that are missing from that oxygen. Okay, that last oxygen has 6 minus. How many lone pairs are around the right oxygen?
4.
This pair is with that oxygen. This pair is with that oxygen. This pair is with that oxygen. How many lone pair electrons?
6 then.
How many bonding electrons?
2.
So my charge on this oxygen is 0. This sulfur is a +1. This oxygen is a -1. The addition of all formal charges should add up to the charge on the entity you're looking at. SO2 has no charge. 0 plus 1 minus 1 equals no charge. So this is simple math, guys. Are we getting an understanding of formal charge?
Is this also like the bonding order?
No.
Oh, okay.
Bonding order has to do with molecular orbital theory.
Okay.
And bonding order, again, if you haven't been taught this, then put your hands over your ears and say dead kitty. Bonding order, you take the electrons in the bonding orbitals and you subtract the bond.
Mm-hmm. It sounded, the math sounded similar. That's why I was asking.
No, it's different theory.
Okay.
Different theory.
All right, thank you.
Okay, now, I introduced that there because I want to start to talk about violating the octet rule. Sometimes things do not make chemical sense. And if they don't make chemical sense, they can't exist. Lewis is fallible. So you do not absolutely have to have 8 electrons around an atom. It's going to occur, this violation of the octet rule is going to occur because you have an overabundance of electrons, or sound chemistry dictates that you violate the octet rule. BF3 exists. Boron has 3 valence electrons. There are 3 fluorines for 7 each. I've got a total of 24. So if I'm drawing my Lewis dot structure, I'm going to put my 3 fluorines around my boron. I'm going to connect them with 3 bonds of 2 electrons each. That means I have 18 left. My next rule says I fill up all the terminal atoms with electrons. Guys, you're going to have to bear with me because it's extremely difficult for me to draw the dots in here. As you saw in the last slide, they get off a bit. So you're just going to have to bear with me that this fluorine has 2, 4, 6. This fluorine has 8, 10, 12. This one has 14, 16, 18. So each one of these fluorons is filled up with electrons. Now, normally what you would want to do is take 2 of the electrons and put it down and make a double bond. Correct, ladies and gentlemen?
Yes.
Yeah.
That's what you would want to draw a molecule like this. There's a trouble with this. Okay? These 2 fluorines are going to have a formal charge of 0. They're not the problem. In my boron has 3 valence electrons, no lone pairs, and it has 2, 4, 6, 8 bonding electrons. So if I determine the formal charge on my boron, I have 3 minus 0 plus 8 over 2. My boron has a -1 charge. If I look at my right fluorine, remember there are 2 lone pairs out here. So the formal charge on that fluorine, normal valence 7 minus, it has 4 lone pair electrons plus 4 bonding electrons. So I have 7 minus 4 plus 2. The fluorine is a +1. Now riddle me this, Batman. What is the most electronegative atom in the periodic table?
Fluorine.
Is fluorine ever going to be a positive charge?
No.
It will never be a positive charge. At most, I can have 1 fluorine with another one, and I have a formal charge of 0. It will never have a positive charge. So BF3 cannot exist like that. It has to exist as 3 single bonds. And crystallography proves that this compound exists as a trigonal planar shape, with all of the bond lengths being the same. So evidence supports this as being the right molecular structure for BF3, even though it violates the octet rule. Does that make sense, ladies and gentlemen?
Yes.
Okay. All right. You can also have a situation where there are extra electrons around the center atom. Now, do you recall quantum mechanics? when you're filling up atomic orbitals. You go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, right? So you have extra orbitals in the third shell that are Ds that are not occupied yet. Does that make sense? There are extra D orbitals there. Does 2p have that luxury? Is there a 2d?
No.
So everything on the 2 level of the periodic table must adhere to the octet rule. If you're down, the next level down, you can dip into those d orbitals and put extra electrons around the center atom. And you're going to do it because you have to. So I have a compound, ICl5. Now, if you're familiar with halogens, how many valence electrons are around a halogen?
7.
7. So literally speaking, halogens can be bonded to one other thing unless they're the center atom. If I have a compound, ICl5, which does exist, if that's a compound, then something has to be in the center and everything goes out from there. Does that make sense, guys?
Mm-hmm.
So iodine is the least electronegative. I'm going to put that in the center. I've got 5 chlorines that have to be around it. So I'm going to put them around, and I'm going to put 2 electrons between each as bonds. I started off with 42 valence electrons. Now I've used up 10. I have 32 left. My next step, I'm going to put them around the terminals. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. I have used up 30 electrons, putting them around the terminal atoms. I have 2 left. My rules dictate, where do those 2 go? SO2, we had an extra 2 electrons. Where did they go in that case?
On the central atom.
They go on the center atom. So I'm going to have to take those 2 extra electrons. They have to go somewhere. I've got to put those 2 extra electrons on the center atom. So my Lewis dot structure is going to look something like that. Inert gases will react. Inert gases will make compounds. XeF4 does exist. Got to count up all the valence electrons. 8 come from xenon. 4 times 7 come from fluorine. I have 36 valence electrons. How do we set this up? How do we write this particular compound? Start the Lewis dot structure. What goes in the center?
Xenon.
Xenon goes in the center. The 4 fluorines go outside of it. And I have to put 2 electrons between each one of them. I had 36. How many did I use up?
8.
8. 36 minus 8, I have 28 left. Where do those 28, where do I start to put the electrons on next?
Fluorine.
2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've used up 24 of my remaining 28. How many do I have left?
4.
Where do they go?
1 on each fluorine.
No.
On the XE xenon.
When you have extra electrons, they go on the center atom. So literally speaking, I have 2 lone pairs on that xenon. Questions about how to make Lewis dot structures that violate the octet rule? Okay. I'm going to put a new slide. Okay. Now, I'm going to do this real quick. No, I'm not. I'm going to do something else. Rather than do this, why reinvent the wheel? Okay, here we go. Okay. I have 3 structures, C and O. I can make C and O in 3 different forms. These are all valid Lewis, C and O minus. These are all valid Lewis dot structures. Double bonds between the C and the N and the O. Triple bond between the C and the N and single bond between the N and the O. Single bond between the N and the C. Triple bond between the N and the O. I'm sorry, I need to move something because it's offending me. Okay, now if I determine the formal charges on the C, N, and O, I get -2 for the C, +1 for the N, 0 for the O, if they're both double bonds. If I have a triple bond between the C and the N and a single bond between the N and the O, my formal charges are -1, +1, and -1. If I have the triple bond between the O and the N, my formal charges are -3, +1, and +1. Do you trust me that these numbers are right? If not, we can go and figure it out. Now, which one is the best structure? The best structure, you use 2 parameters. The first parameter is the least amount of formal charge on all of the atoms. We have to consider all of them. We're not adding them all up. We're looking at each individual atom to see how much formal charge is on that individual atom. That's the first parameter. The second parameter is they have to adhere to the electronegativity rules. In other words, if you have a negative charge, that negative charge is going to go on the more electronegative atom. So, based upon these 3 formulas, which one has the least amount of formal charge?
Would it be the second one?
The second one. Okay. This one has a -2 and a +1. Even though each one of these have charges on them, that is less offensive than this one, and especially not this one. The other thing is, look here. This one has an oxygen, which is the most electronegative of these three elements, and it gives oxygen a +1 charge. So it's not going to work. Does that make sense to you guys?
Did you say we're looking at each individual formal charge? Like look at C, look at N, look at O, and compare
Yes.
the three different structures?
Yes.
Numbers. Okay.
Let's look at CO2. I'm going to draw another one for you. Layout. Okay. I have a couple ways to draw CO2. What happened there? What are we doing? Boom. Okay, that's one way I have of drawing it. I have another way. Okay. Again, sorry about this. It's just all right. Finally. All right, we're going to figure out formal charges. Valence electrons around oxygen. Come on. Quicker you answer this, the quicker we get out of here today. Valence electrons around oxygen.
6.
Lone pairs around this oxygen. Lone pair electrons.
2.
4.
4, not pairs, lone pair electrons. How many bonding electrons?
4.
So what's the formal charge around this oxygen? 4 minus 4 plus 4 over 2. What's the formal charge on this oxygen?
+2.
4 plus 4 over 2 is what?
4.
4.
4 plus 4 over 2.
4 plus 4.
4.
It's not 4.
Isn't
4,
4 plus
I'm
4
adding
is
something
8?
to 4. How
Oh.
can it be 4?
6.
6. So I got 6 minus 6. What's the charge on this oxygen?
0.
0, right?
You're not dividing the entire thing by 2, just the last 4, correct?
Yes, correct.
Oh, okay. That's
So how many valence electrons are around carbon? Normally, how many are around carbon?
4.
4.
How many lone pairs are around that carbon?
None.
How
0.
many bonding electrons are around that carbon?
8.
8.
So I got 4 minus 8 over 2. What's the charge on that carbon?
0.
Mm-hmm. And this oxygen is the same as this one, so it's also going to be 0. Now, let's figure out this oxygen. Again, valence electrons on oxygen, how many?
6.
6.
Plus lone pairs around this oxygen. No, don't pay attention for a second. Lone pairs around this oxygen. Lone pair electrons.
2.
2.
2. How many bonding electrons are around this oxygen?
6.
What's the formal charge on this oxygen?
+1. Wait.
All right.
6.
Let's figure the carbon. Valence electrons.
4.
Guys, I'm hearing one person answer this. How many lone pairs are around this carbon?
None.
Still hearing one person. How many bonding electrons around this carbon?
8.
So what is the charge on that carbon?
0.
Let's figure out the last oxygen. Six valence electrons, 2, 4, 6 lone pair electrons, 2 bonding electrons. This oxygen is going to have a 1- charge. So between these two structures, which one has less formal charge?
The first one.
So that is the structure that is the preferred structure. You're also going to get this where the amount of charge is the same, but the charge is the same, but the charge goes on the wrong, and we'll go with this. If, let's just say, for kicks and giggles, if these are my two structures, and I figured out the formal charges were this. This is not true, by the way, but if I did figure out the formal charges, and this one turned out to be the nitrogen -1, the carbon 0, the oxygen +1. And this one turned out to be the nitrogen +1, carbon 0, oxygen -1. Which one would be the preferred structure? And why?
The second one?
Why?
Because oxygen's the most electronegative, so it has to be a negative
Did
charge.
everybody see that? Okay.
No, I don't.
Okay. Max, was that you?
Yeah. Yep.
Okay. Now, there are two rules for determining what the best structure is. One is the amount of formal charge. Did you get that aspect of it?
What do you mean?
Okay. This is the example I use for that. Okay. Do you see that this has more formal charge than this does? This has the least amount of formal charge as compared to this molecule and this one.
How do you determine that? Like you just add those up?
You just kind of like look at it and get a feel for it. That's the best way I can tell you to do that, Max. This one has a -2 charge. Do any of these have a -2 charge?
No.
So therefore, this molecule, by the fact that it has one -2 and a +1, is going to have more formal charge than this one. It's harder to get, it's harder to pull that it's harder to push that second electron on the carbon than it is to just take one away, right? Does that make sense, Max? You're rolling your eyes.
Yeah, I don't really get this stuff. Sorry.
Max, I will talk, if necessary, I'll talk to you later then, okay?
That's fine.
The other part, that's the first thing. The amount of the formal charge on the individual atoms is the first determiner. The second determiner is that the negative charge is going to be on the more electronegative element. So I figured out the formal charges for my 3 elements here. In my first compound, the negative charge is on nitrogen. In my second compound, the negative charge is on the oxygen. Which element is more electronegative, nitrogen or oxygen?
Oxygen.
So therefore, it's going to want to have the negative charge. Therefore, this structure is more stable than the other one. Does that make sense, Max?
Yeah, that part does.
All right, I'll get and try and get the other one back to you. All right, questions about Lewis dots? All right, we're going to stop sharing, then we're going to get on to VSEPR. Max, do you have a brother?
Only child.
Forget you. Javier, do you have a brother?
Yeah.
All right, Javier, when they packed the kids in the car and you got shoved in the back seat, did you and your brother sit right next to each other? Real close to one another, like you were touching each other? Is that what happened, Javier?
No.
You guys were plastered against the windows, right? As far away from one another as you can get, right? Atoms are the same way. They want to get as far away from one another as possible. So basically, we developed a theory based upon this fact, and you want to get the minimal amount of electron pair repulsions you can. You want to get the atoms as far away from one another as possible to minimize these electron pair repulsions. And that is what is going to determine the shape of your particular molecule. Is this kind of making sense, guys?
Yeah.
Max?
We did VSEPR really early on in lecture and I never got it down. So
okay, well, let's try it again, all right? Would you agree, Max, that you don't want to be as close to people as you may? If you have a choice to be this close or this close, you're going to be further apart, right?
Yeah.
And you're going to kind of work it. If you ever look at people in conversation at a party, there is a level at which they're comfortable at. And if somebody moves closer to you, that person is going to gradually move around. Or better yet, if you're in an elevator. If you have one person in an elevator, they're generally in the center. You put another person in there, you kind of go to the corners. Does this make sense, Max?
Yep.
The same way with atoms. if I have two atoms around a center atom, if I put them like one here and one here so that I have a 90 degree, are they going to want to drift apart further from one another? Max?
I don't know.
Okay. You have one atom that's right here. That's our center atom. That's right at this corner of this white block. One of the atoms is over here. The other atom is up top. Are these guys going to push away at one another?
Yeah.
Are they going to push? They're going to push. So these two are going to push apart. And they're going to push so far apart from one another that they're going to go beyond the magical line. And when they get at the magical line, they're not going to go beyond that, because if they go beyond that, they're getting closer on this side. Right, Max?
Yeah.
They're going to push away until they're as far away from one another. And if they try and go further away, they get closer on the other side of the line. So they're going to be 180 degrees apart from each other. Does that make sense, Max?
Yep.
Okay, so in order to make these such determinations, we need to find out how many things are around the center atom. And we do that by defining something called electron clouds. You can call them electron domains. You can call them domains. It doesn't matter what you call them. You just need to be able to count them. An electron cloud, every lone pair around that atom is one cloud. Every lone pair. Each single, double, or triple bond counts as one electron cloud. So if I have a triple bond on the left side of my center atom and a single bond on the right side, the triple bond counts as one electron cloud. The single bond counts as another electron cloud. Lone pairs are any electron pair that's not involved in bonding. They have they're the exclusive property of the atom at which that lone pair has been put. Bonding pairs are the pairs of electrons that are involved in bonding. They're the electrons that are between the atoms. So if I'm looking at this particular molecule, I have one domain from the double bond, one domain from the right single bond, one domain from the left single bond, and one domain from the lone pair. This molecule has 4 electron domains about the A atom. Is that making sense to you all? Now, I'm going to get to that later. So what we have to do is we have to look at the electron domains around the center atom to determine an overall geometry that I'm going to call an electron geometry. So even though ammonia has only 3 atoms bonded to the nitrogen, it also has a lone pair. So I've got to incorporate that lone pair into the overall structure of my ammonia. There's no other way to do this but memorize it. If I have, these are electron clouds around the center atom. 2 electron clouds, the electron geometry is linear. 3, trigonal planar. 4, tetrahedron. 5, trigonal bipyramid. 6, octahedron. I'm just talking about the electron geometry. This is the first one we need to determine when we're determining the overall shape and ultimately the polarity. So molecular geometry is different from the electronic geometry. When I'm dealing with molecular geometry, I'm only dealing with the arrangement of the atoms. It doesn't count electrons. So if I'm looking at this molecule of water, I can see the hydrogen, the oxygen, and the other hydrogen, and I can't see the electrons. What the electrons do is they push the hydrogens away from being a linear molecule. They push them down. So when they push them down, the overall shape is going to be bent. So when we are dealing with molecular geometry, we have to deal with something called the bond angle. And that's the angle between the two adjacent atom, center molecule, or center atom, other atom. If I have a linear, this bond angle is going to be 180 degrees. If I shove another atom in there, the atom I'm shoving in there pushes the other two up a bit. And when it pushes it up until these two start to repulse one another. And when they start to repulse each other with the same force that this one is pushing them down, the bond angles have become equal. Trigonal planar, that's going to be 120. I shove another atom in there. 3 points make a plane. I shove another atom in there, I can invoke the third dimension. I shove another atom straight down on top of this. What it does is it pushes the 3 that are in the plane down into my screen. So this one on top pushes the other 3 down until they start to repulse each other. And when it does, I end up with the shape called the tetrahedron. I shove another one in there, and what that does is it makes a plane that has 3 angles of 120, and we have 1 atom on top and below this plane, so that angle is going to be 90 degrees. I shove another one in there. That's octahedron. All the angles are 90. So let's deal with what's happening when we have atoms and lone pairs. Understand this. If I have no lone pairs, the electronic geometry is same as the molecular geometry. If I have 2 atoms around my center atom and no lone pairs, I have a linear molecule. 3, I have a trigonal planar. 4, tetrahedron. 5, trigonal bipyramid. 6, octahedron. If I have no lone pairs, my electronic geometry is the same as my molecular geometry. When I have a lone pair, what happens is I can't see the electrons. So if one of these sites is occupied by a pair of electrons, all I can see is the white ball, the blue ball, and the other white ball. My geometry is bent then. If I have 4 things around my center atom, 4 electron clouds, my electron geometry is tetrahedron. If all 4 sites are occupied by atoms, my molecular geometry is also tetrahedron. If I have 1 lone pair, I can't see the electron pair that's on top. All I can see is something that looks like a 3-sided pyramid. So my shape is trigonal pyramid. I take another thing away from my tetrahedron. I now have two electron pairs I can't see. I have a bent molecule. Now, electron clouds push with greater force than electron clouds from lone pairs push with greater force than electron pairs in bonds. So in effect, what happens is when I have this one lone pair on top of these three atoms, it pushes these down with more force than the three atoms repulse each other from one another. So my bond angle for the trigonal pyramid is smaller than the original 109.5. It turns out to be about 107. If I put a second pair of electrons there, it pushes it down even more. So when I have a tetrahedron electronic domain and I have two lone pairs, my bond angle is going to be even smaller. It's going to be 104. 5 things. Electron domain around a center atom. If all 5 are occupied by atoms, my shape is trigonal bipyramid. If I have one lone pair, the shape is called seesaw. And if you kind of want to think about it this way, this part acts as a fulcrum and this can kind of go up and down. Some chemists have better imagination than others. If my electronic geometry is trigonal bipyramid, I add 2 electron pairs, my shape becomes T-shaped. Because all I can see are these 2 going straight up and down and this one off to the side. 3 lone pairs, it becomes linear. Now, just as a matter of semantics, guys, I specifically called them trigonal bipyramid rather than trigonal bipyramidal. Anybody know the difference between trigonal bipyramidal and trigonal bipyramid? Trigonal bipyramidal is an adjective. Trigonal bipyramid is a noun. That is the only difference between the two. Okay, that little sidelight. If I have 6 things around my center atom and they're all atoms, they're all atoms, then my electronic shape is octahedral. My molecular shape is also octahedral. One of those turns out to be a lone pair. I have a 4-sided pyramid. So I call that a square pyramid. I take another pair away from the, put another lone pair in there in place of an atom. I now have 2 lone pairs around my center atom. The best shape I can come out of this is a square planar. So when you're doing VSEPR, you have to draw the Lewis structure first because you need to know how many clouds are around a center atom. Have to. Then you count the domains around the center atom and you apply the electronic geometry to that. Then what you have to do is you mentally have to kind of subtract out the lone pairs from that. Or you have to memorize the chart. Now, if you're having trouble thinking about this spatially, I can understand that. You can buy a molecular model kit, and if you're going on to organic, you may actually use it again there. But the kits are like $350 to $500. What I would suggest that you do is buy a bag of pretzel sticks and marshmallows. It does the same thing. Then when you're done, you can eat the profits. If you want to, guys, I will upload this slideshow in there. I'm not going to go through each and every slide, obviously. What I'm going to do right now is attempt to do polarity. With the time that is remaining. Okay, polarity is a physical property of molecules in which a molecule will rotate in a magnetic field based upon unequal charge distribution in that molecule. Basically, you put the molecule in a magnetic field, it rotates to have the positive end of the molecule face the negative end of the magnet, and the negative end of the molecule face the positive end of the magnet. That's all polarity is. What happens in the molecule? Polarity is defined by this rotation, but what makes the rotation is an unequal charge distribution in the molecule. So the molecule becomes charged. If the molecule becomes charged, it gets attracted to other molecules that are charged. So a polar molecule will be attracted to other polar molecules, and because they have charges, ionic molecules. A polar molecule will be repelled from non-polar molecules. Similar circumstance, non-polar molecules will attract other non-polar molecules. Non-polar molecules will repel polar and non-polar and ionic compounds. And what basically this means is polar molecules dissolve polar molecules and ionic molecules. Non-polar molecules dissolve non-polar molecules. Like dissolves like. So what makes a molecule polar? If I'm dealing with a chemical bond and I have two different atoms, they have a difference of electronegativities. The atom that is more electronegative will control the, sorry, I have to draw that because it makes sense. The atom that is more electronegative will control the electrons more. In other words, the electrons in an HF molecule, the electrons spend more time around the F than they do the H. So there is a charge distribution. The hydrogen end will be positive. The fluorine end will be negative. So you look at the electronegativities of the atoms to determine whether or not your particular bond is going to be polar. All right. In order to have a polar molecule, you need polar bonds. Now, you got to see how those polar bonds are distributed within the molecule to see whether or not you get an overall charge distribution. In medieval times, they had this quaint little custom called drawing and quartering. Basically, they used to hitch up each one of your limbs to a horse and yell, "Giddy up." Well, the horses tore off your limbs and they went flying, but your torso stayed in the same place. Your torso didn't move. So if I have a molecule that is, say, a tetrahedron shape. Each one of these atoms, if each one of the atoms has a chlorine in it, then I got one chlorine that's pulling the electrons straight up. But I got these three that are pulling it down. The effect of this one pulling it straight up and these three pulling it down at an angle offset one another. So overall, I can't say that this end's negative or this end's negative. It's kind of negative all around the outside. So if it's negative all around the outside, if I put this molecule into a magnetic field, it's not going to move. Because if this one is negative and it wants to go towards the positive end, these three are also negative and they get repelled from the negative end of the magnet. So overall, I have no net movement. Overall, this molecule with 4 chlorines around the carbon doesn't have any movement. It is not polar. It is not polar because it is symmetrical. So literally speaking, in order to be polar, a molecule A has to have polar bonds, and B, it has to be asymmetrical. How would I make, if each one of these is occupied by a chlorine, how would I make this molecule asymmetrical? What would I have to do to it? I got to change the molecule some way. How am I going to change it?
Would you have to add something, a chlorine?
If I add a chlorine to this, I'm going to make a trigonal bipyramid molecule. And literally speaking, if there are all chlorines around there, I'm going to find the trigonal bipyramid, then they're all going to equally and oppositely move away from one another. So I can't do it by adding a chlorine. How can I do it though? Do all of the atoms have to be chlorine?
No.
Can I replace the chlorine with a hydrogen?
Yeah.
If I replace the chlorine with the hydrogen, is the molecule symmetrical anymore?
No.
I got 3 chlorines down here, 1 hydrogen. Is it symmetrical 360 degrees around it?
No.
No.
So if I have 1 hydrogen and 3 chlorines down here, it's no longer symmetrical. Now I want to draw something. When you guys draw, where is this at? When you guys draw, you are going to draw that something like again, bear with me. Oh, good. If you draw this molecule, Lewis dot structure of this molecule, this is what you're going to end up with. Is this molecule symmetrical?
Yes.
How many vote? Okay, guys. I want you to go on your bar and on the bar, where's that at?
The chat thing?
No, I wasn't using the chat thing. I was going to do the oh, crap. Crap. Are you still seeing the screen?
Yeah.
You're still seeing the screen?
Yep.
I can't see the screen. Yeah. There we go. I can see the screen again. All right. Javier, symmetrical or not?
I think so. It's symmetrical.
Max, symmetrical or not?
It looks symmetrical to me.
Tren?
Yep, looks good to me.
Samir?
I think so.
Charlie?
Yes.
Faye? Everybody, is there anybody that thinks that this molecule is not symmetrical?
I don't know. I'm still drawing the Lewis diagram.
The Lewis dots up here. Is there anybody that does not think that this molecule is symmetrical? Have I
It's not,
intimidated
because
you
you
yet?
said it's not.
Have I intimidated you yet?
Kind of. I mean, it's a dichloramine structure, right? So it's a
All right, let's think about this. What is the real shape? What is the real shape of CH2, Cl2? Is it not a tetrahedron? Four things around the center atom, right?
Yes, it is.
So place them. You put two chlorines here, right? Two hydrogens here. Is that molecule symmetrical?
Yes.
Two chlorines on this side. So
Oh,
this
sorry.
side of the molecule has a whole bunch of chlorines. This side of the molecule has a bunch of hydrogens. Is it symmetrical?
No.
it doesn't really look like it.
Can you put two chlorines and two hydrogens around here such that it will be symmetrical? Put them anywhere you want.
I mean, if you could put them anywhere you want, you could probably have them all in the same direction and whatnot, right?
Put them over here. Put the chlorines over here, the hydrogens over here. That means this side of the molecule that's facing in towards the screen has the chlorine side, and this side has the hydrogen. You are always going to have a chlorine side and a hydrogen side. So CH2, Cl2, even though when you draw the Lewis dot structure, this looks like it is symmetrical, when you apply it to the actual shape, the actual tetrahedron shape, it is asymmetrical. So you got to be aware of this kind of spatial thing that you're dealing with here. Okay, I've been talking for about 2 hours and so. That's literally all I really wanted to talk about. There are other aspects that you have to know about eventually, such as resonance and isomers that I haven't gotten into, but there's only so much I can really get into in 2 hours. If you're that curious, I will be happy to go through and talk about isomers and resonance after this. But after about 2 hours, I figure you're pretty well fried. Any questions on anything I've gone over today? Did it kind of help?
Yes, it did.
Yeah, it did.
I'm not looking for a pat on the back, guys. Tell me if there's something that you're still out in left field about. If I was looking at these slideshows, that's an important slide. And this one and this one. Extremely important slides. Because that's going to give you the geometry. Buy yourself a bag of pretzels and marshmallows. Work it out. Other than that, is there anything else I can do for you guys? Final.
Nothing that I can think of.
The final is going to be next week at this time. It's open at 8 a.m. It closes at 5 p.m. All right. Is there anybody that is constrained by those time parameters? I'll be honest, my Wednesday night class, I've got it open from 8 till 8 or 8 until 10, but that's because it's an evening class and a lot of them work during the day. If anybody is constrained by the 8 to 5, let me know. I will open it. Now, how would I study for that? I would go back and
Going over
look.
our lab notes.
I'm sorry, question?
You said how would we study, and I said by going over our lab notes.
Pretty much. I would go back, get the original data that the course provides you with. And I would take that original data and I would do the determination, much like you did it in the results. The final mimics the individual laboratories in that fashion. Pretty much, you're going to be guaranteed you're going to have to standardize a base. Pretty much, you're going to have to take that standard molarity of your base and determine the mass percent of an antacid tablet. Pretty much, you're going to probably have to do an RF. Pretty much, you're going to have a graph with a slope, and you are going to have to use, the graph is absorption versus concentration. You're going to have to use that slope and an absorption to determine what your concentration is. Densities, be aware of that. Be aware of this stuff. Generally speaking, guys, I have seen where the final blows a grade for people. I have seen that. I have seen where the final pulls, on one occasion, a final pulled somebody up from a C to an A. But they had a absolutely perfect score on their final. It is possible. Try not to blow the final, as I guess. Do not take it with total disregard. You do need to study for it. And that is literally my best advice for how to study for the final.
Is it going to be open notebook for all of it or just?
Okay. Yes, you're allowed to use your lab notebook. If your lab notebook is in separate pages because you haven't bought a lab notebook, and I can't make that determination based upon your submissions. If that is the case, then I have to allow you to use separate papers as your lab notebook. Are you reading between the lines, ladies and gentlemen?
Absolutely.
Yes.
So you're allowed to have, I consider this to be an open book, ladies and gentlemen. If you wanted to make these pictures and put these into your notes, there's nothing that I'm going to do to prevent you from doing that.
Thank you, Professor.
Other than that, I don't know what else to say. I probably will hold off 2 days. I will grade the finals and I will hold off 2 days before I enter the final grades into the permanent grade.
So we can take it anytime between 8 and 5 on Thursday?
Yes, I believe it is capped off at 3 hours. So if you want the entire time to take the test, you better start it by 2 p.m. I'm not entirely certain, but it may cut you off exactly at 5 p.m. Okay, Charlie?
Okay.
Thanks, Professor.
Anything else? I do have one more thing, ladies and gentlemen. It has been an honor to teach you this entire semester. What I normally do is as you're leaving the class, handing in your final, I make sure that I shake the hand of every student I have. You guys have been a good group. I've enjoyed this. I really have. You've made it easy for me with your curiosity and with your asking questions. That helps the teacher, believe it or not. I really wish you the best of luck in the future. If I can help you, remember, you still have my phone number. Feel free to call that, okay? Other than that, ladies and gentlemen, good luck to you all.
Thanks so much, Professor. Have a good one.
Take care.
Thank you. Have a good day.
Have a good one.
Take care.
Thanks for the semester.
Take care, guys.
Thank you, Professor.
Take care, Trin. Dudley, you still in here? Trin, you still in here? Dudley? Dudley, I'm sorry, but I got to go. I have a life.